All right, let's get started. So today we're actually going to be, and if you had been in the physical lab, you actually could have done the physical lab where we're actually having a prime mover, some sort of device, driving a synchronous machine so that we could actually generate voltage. And it can be any prime mover we want. We could have a hydroelectric facility, we could have a wind turbine, we could have gas turbine, steam turbine. It doesn't necessarily matter. We just need something to apply a torque. And what we're going to do today is apply a torque through this 4-quadrant dynamometer slash power supply. Okay. So this one's a little bit unique too, because there's an on-off switch here. Hopefully y'all can see that. And normally if we were in the lab, we'd have to plug that one in to get power, but I guess they had modified it a little bit, the folks at LabBoat. So you can go ahead and do that. So while you're getting your station set up, I'll actually show you. So 4-quadrant just means you can actually get it to generate power, or I shouldn't say generate, convert electricity from electrical to mechanical or mechanical to electrical. So that's what the quadrants are. You can go in any direction that you want. It also can act as a load, mechanical load, or it can drive the system to whatever we need, which is perfect for us because we're trying to drive this synchronous motor generator set that we have over here. So, excuse me. So there's some knobs and buttons over here. We don't have to worry about that because once you turn the power switch to the on position, you can actually bring up this this sort of a web app that allows you to go ahead and change voltages, or not voltages, change speed, torque, and power through this device. Now, one of the things that you're going to want to do is you're going to want to configure this to either clockwise or counterclockwise. It doesn't necessarily matter, but you want it to maintain a constant speed. And in this case, I selected a clockwise constant speed prime mover, which means now I can go ahead and set the speed to whatever value I want. So I set the speed to 1800 here. I could have certainly used this knob to manage to go up or down, but since I'm going to try to maintain it at 1800 RPM for most of the lab, I can do that here. There are steps where you're going to go ahead and set it at 200, go to 400, 600, all the way up to 2000, but you're going to go ahead and have that configured here. Okay. So that's sort of the prime mover part of it. That's essentially all we really need to do with this. We do need to wire it correctly. So you can see that I ran 120 volts DC over here. And I'm going to zoom in a little bit because on this device, there's actually some capability of some data acquisition. So if you wanted to, you actually could go ahead and do some speed control over here, but we're not going to do that. We're going to just simply configure this so we can use our data acquisition device to get some additional parameters. You'll notice analog outputs, you have torque, and this is a little bit hard to speed, but it says analog speed is output as N, which is the actual speed. So I can run the torque. If you look closely on the analog inputs for a 4-channel DAC, you do have this channel, this T, 7/T. So I'm going to run channel, the torque channel to channel 7, and the speed channel, I'm going to run it to channel 8. Now, what these are doing is they're outputting an analog voltage. It's going to be, I don't know, 5 volts or something like that. So because we have a voltage source there, we have to make sure that we have to provide a reference for it. So if you look closely, you'll see that there's an analog common. We need to run that here to our analog value. All right. So what I'm going to do is I'm just going to show you how you can use that information. So I'm going to start this unit spinning. So I'm going to bring up the screen here, and I'm going to hit the start stop button. And if you go over here, you'll actually see how the speed is going to go up to around 1800 RPM. So you can see that on the screen. But if you recall, we're doing a lot of data collection where we're trying to measure voltages and currents and all that stuff. So I can record this manually. But another thing that I would like to do perhaps is I'd like to use my data acquisition to record that. So if I click on my meter and bring that over here, you can see that I have a torque input and a speed input. So I'm going to set this to continuous refresh, and you can see that it's running at 1800 RPM. If I want to change the speed, 1600 RPM. Go back to my other indicator. Oops, here. And now I'm running at approximately 1600 RPM. Okay. So we'll do more and more of that as we go. But the first thing we're going to do is we're going to set up the synchronous machine so that it can actually have some some prime mover. So the first thing I'm going to do is turn off the power, and you'll see that this starts to slow down. You can also right click on this, and you can see it says stop the motor. Just also too, this actually indicates the direction, because you can't necessarily tell by looking over here at what this is doing. So it's basically just spinning in the air, but it's spinning in the air in the clockwise direction. So I'm going to stop the motor, and you'll see that that stops. You get no information. Now, excuse me, I'm going to lower the front panel. And why is it that I lower the front panel? Because these two devices have to be mechanically coupled to each other. And this is a pulley right here, and I need to connect this pulley. So if I drag my mouse, you can see the black line that's going across, and drop it in the center, you'll notice that the pulley here is sort of shown, sort of animated, if you will, or just a cartoon, but you can actually see that the belt actually connects these two. So now when I raise the front panel here and raise the front panel here, and I get this unit spinning again, you'll see that both of these are rotating. So we'll do that really quickly here. We'll flip on our switch. We'll turn this power supply on, bring that up. We'll set it at 1800 RPM after I move it to a constant speed. Run that at 18. And then now, if I look over here, hit the start stop. Why is spinning? Usually should show this as spinning. Let me just make sure that it is in fact spinning. Oh, now I hit start stop. I guess I didn't enter it in all the way. Now you can see that both of those units are in fact running at 1800 RPM. So again, I'm going to switch off the power and stop these, because at this point, I know that I've got the rotation of this. So all I've done now is I provided the mechanical capability of rotating this thing. And since I'm operating this as a synchronous generator, I need to go ahead and have an input mechanical force, which is what I'm getting through this belt. So the next step I'm going to do is I'm going to go ahead and provide, let me zoom out just a little bit. I'm going to provide the DC value that I need. So remember, the synchronous machine has a rotor that needs DC. So I'm going to run a fixed DC to the machine. And you'll notice that this DC is going to allow me to create a voltage once I have the synchronous generator running. A couple of things have to happen. I have to have a unit running, and I also need to make sure I have DC, which this switch here allows me to energize or de-energize the DC field. Then over here, there's a 150 ohm resistor in here, which basically is a way of controlling the speed and controlling the field and either increasing it or decreasing it. So when I see what it says minimum over here, this is the minimum amount of current that goes into the machine. Make sure when you wire this up, you use the DC and not the AC, because this unit doesn't work on AC. That would be an induction machine, and you get all kinds of crazy operation. Now I'm going to go ahead and connect these windings in a Y. So I'm going to drop these here. These here. And now I'm going to run these to my meter. So I'll run E1, E2, and E3. So I have my voltages, and I have to provide my reference. So I just have to run one wire to here, and then the other ones I can just jump across. And here to here. All right, so all those wires are jumpered together. So now if I energize the unit and look at the voltages, then I should see that this unit will start to operate once I close this switch in. So I'm going to go back and whoops, that's the wrong button. Turn this on. Power this up. Again, bring up my screen. And this is going to be clockwise. I'm going to set it for 1800 RPM. And then I'm going to hit start. And now the unit should be running and rotating. So I'm going to wait till I get to about 1800 RPM. Now I'm going to check the metering window. And I'm going to turn on my continuous refresh. And whoops, wrong button. And do you see nothing is happening? The voltages and the currents are 0, but the speed is 1800 RPM. Well, why isn't there any voltage? If you recall, I said that this switch has to be in the closed or the 1 position. Right now it's in the open position, so there's no DC excitation going in here. So there really is no north and south pole on the rotor circuit. There's only a hunk of iron that's rotating around, or a hunk of wire that's rotating around. So when I close this switch, you'll notice that these 3 voltages will go higher. So let's close the switch. And why isn't the voltage? Why didn't the voltage click on? Let me just make sure that there's power here for the DAC. That's on. Oh, this power, I guess, had to be on. I thought that that was on. That's interesting. It almost seems like it tripped the breaker off. So the power was off. Now let's go back to my metering, close the switch, continuous refresh, and now I have voltage. So you see when I toggle this and I go off, you see the voltages go to 0. When I close it back on, now I'm starting to get your voltages. And now I just go ahead and I rotate this. And let me minimize this so you can actually see both. So when I rotate this, you'll see the voltages change. So now if I move to max, then what's going to happen is it's going to decrease the resistance, which increases the current, and watch my voltage increase. So this is the voltage across any individual phase. So each individual phase at this point is getting 120 volts approximately across the outputs. The other thing that might be interesting too is I know this is running at 1800 RPM. I'm just kind of curious what the frequency would be. So if I bring up the frequency, and I'm just going to pick a value over here, let's pick E1. Any voltage that has an actual voltage source is perfectly fine. And you can see that I'm right at 60 hertz. Okay. So I'll also look at the oscilloscope. So let's bring up the oscilloscope. I'm going to maximize this again. And I'm going to look at my voltages. So channel 1 is going to be E1. Wait a minute. I want that to be none. So I want channel 2. Because I want these to be the Ys. Not channel 1. That would cause me to have an x-axis of the voltage. Now I do my continuous refresh. And I did 2 E2s. Apologize for that. Here's E3. And you can see that all the waveforms have about the same magnitude, and they're offset by a certain amount. So if I stop these and I bring my cursors up, you can see here how I can look and see what the relative phase shift is going to be between these two. I like to work with peaks. If you don't like to work with peaks, you can work with 0 crossings, just as long as you're going either on the rising edge or the falling edge. So I'm going on the falling edge of the red, which means I need to do the falling edge for the blue. And then you can see the time difference of 5.59 milliseconds, right? You can see, I mean, it's hard to tell, but it says this is in milliseconds per division. So this is 5.59 milliseconds. Is there a way that you're aware of to how to calculate the phase shift? Because we know that this is the difference in time, but how do you actually calculate the phase shift between those values. Does anybody remember? This is something I believe you would have learned in John's class, but if not, let me go ahead and swap the sharing. All right, can you all see my whiteboard screen?
Yep.
Yep.
Okay. So, whoops, I always forget to do that. Here is just an XY axis. I'm going to put one sine wave in here. And this takes one period to go ahead and before it replicates, right? After one period, then the sine wave repeats, and so you one period. In 60 hertz land, we have a frequency equal to 60. If you remember from physics, that's the same thing as 1 over period. So the period over here is 1 over the frequency, which is 1 over 60, which is 16.67 milliseconds, correct? So that's 16.67 milliseconds, but that's also one other thing that is exactly the same. That takes 16.67 milliseconds, but it also takes 360 degrees to go through one complete cycle because it repeats every 360 degrees. So we know that 16.67 milliseconds must equal 360 degrees. So now I'm going to set up an equality. An equality of 1 is equal to 360 degrees divided by 16.67 milliseconds. And if you remember, my calculated value of 5.59 milliseconds is the actual difference in time. So if I want to convert the difference between two waveforms, in this case, the red waveform and the blue waveform, I know that that takes 5.59 milliseconds on the oscilloscope. But I want to get that in degrees. So the conversion for degrees is 360 degrees divided by 16.67 milliseconds is the same. So I multiply that by 5.59 milliseconds. And of course, MATLAB's not running. So let me just use my calculator. And so I've got 5.59. And I'm not going to bother with e to the minus 3 because I'm going to divide it out. Or multiply it out, I should say. So I'm going to divide that by 16.67. And I'm going to multiply that by 360. And I get about 120 degrees. Okay. So that's the way of using an oscilloscope, which is actually happening in the time domain. This is happening in the real world. That's what our waveform is. We can also go back to our screen, and instead of using the oscilloscope, we can use the phasor analyzer. And the phasor analyzer means we're just looking at voltages. So let's turn on our voltages, E1, E2, E3, do a continuous refresh. And what do you know? All the magnitudes of the voltages are the same, and they're phase shifted by approximately 120 degrees. So you can look at the oscilloscope, or you can look at the phasor analyzer and confirm that those are producing voltages 120 degrees out of phase with each other. Okay, so I've been babbling on. So let's just see where we're at in terms of in the lab, what you should be able to do. I showed you how to calculate phase shift. You should be able to do up to part 7 in the oscilloscope and part 8. So you should be able to go all the way through up to and including step 9 before we'll get back to it. So I will pause for any questions at this moment. And if there are no questions, I'll let you get started on the lab. So any questions to this point?
Nope.
Paul, could you just show what you have for wiring with the like power supply and generator?
We'll zoom out a little bit. Is that enough? Or, I mean, that's all the wires right here that I need. So you'll notice, since this is a synchronous generator, I don't have any AC connections. but the output voltage over here is an AC voltage. You can see I have that here. So I'm not using any of the connections on the power supply to produce AC voltage. But let me minimize that. I can also do, if this is helpful, I can do a screenshot. Oh, sorry about that. I'm going to do a screenshot and I will post this so you all can zoom in and out to the chat. Is it?
Thank you, Paul. That's actually very helpful.
Yep, let me send it right here. Where's the chat? Here we go. Okay, I just posted a screenshot of that now. Does everybody get it?
Yep, it's there.
And hopefully there's not too many wires. I did include the data acquisition connections there, but you can take a look. So unless there's any further questions, I'll pause the video and give you all, I don't know, how much time we want to do. Let's say we'll check back in around 1:30 and see where everybody's at and ready to proceed from there. Sound good?
Sounds good to me.
Okay, but feel free to ask questions. If I need to, I can restart the recording. So I will pause the recording and wait for any comments or questions, or I'll check in about 10 minutes. Okay, how's everybody doing? Anybody still cranking out the first parts? Do we still need more time or?
Oh, I'm not able to get any torque or power. I just have speed, but everything else is zero. I don't know what's going on there.
You're not reading any power indication? It's not.
No, or voltage.
Did you close your switch?
On the generator?
Yes.
Yeah.
And you got it rotating?
Yeah, it's rotated. It looks like it is on there at least.
Would you be willing to share your screen so I can help you? Or I can meet you in a separate waiting room if you're uncomfortable sharing your screen.
I can share.
Okay. Go ahead. You should be able to share
Yep.
it now. Okay.
You seeing that there?
Yeah. Well, it tripped. You see the reset button? It's red.
On which one? Oh, down here?
Yeah.
South edit. Okay.
So you must have overloaded something perhaps.
Okay. There we go. Interesting.
Are you getting any power now?
Yeah. Yeah.
Okay.
I guess I didn't realize it had that that trip
Yep.
function. All right.
Okay. Thank you. Does anybody need time or shall we proceed?
Give me one more minute and then I'll be good.
Okay. Okay, I think it's been about a minute. Does anybody want more time or can we proceed?
I'm all set now.
Okay. So the next step is we want to put a resistor in series with our excitation system so that we can get the current values we want. If you look closely, there's already a resistor in here. We have to add another resistor to go ahead and do that. I'm actually going to add two resistors because what we found in lab this morning is it is helpful to have a couple of them. So I'm going to disconnect from my power here. I'm going to put these, as you can see, I just put them in series with each other, and then I'm going to run those through here. And then I got to close the circuit. So I'm going to energize two 1200 ohm resistors here. So now I can go ahead and I can measure the current. So, before I did that, I should have actually run it. So I'm going to run that into my meter here, right? So I've got to run that and then continue on in a series circuit. So now I'm going to go ahead and I'm going to enable my current here. So let's turn these off because these are not doing anything. And you can include the torque, but you're really not going to use it this time. Don't forget, this current is a DC current, so switch it to DC, not AC. This is your field current. There's no AC current coming out of the machine because there's no load. All we have are multimeters in here, so there's no effective load on here to draw any current. So now I'm going to close the switch, and I'm going to monitor what my current is, my field current, and you can see, oops, as I move these around, make it so you can see a little bit. I guess maybe this is the max I'm gonna be able to see. I can change position of my switches. I can toggle things. I can do a bunch of different things. So right now I have 1200. You can see I have 0.56. So I can go ahead and I can adjust this down. So I can get a very little current here. So you can see that in this case, I'm only getting about 0.55 or 55 milliamps. And if you look at the lab handout, it says to do it with it open circuited or 0 amps. All you need to do that is you can just open the switch, which is 0 amps, right? But over here, I'm getting 55 milliamps. It's fine if you want to go ahead and tweak it a little bit. So if you really wanted to be super precise, you could drop down this over here and run this connection here and click this one on. And now we're at 0.38, and then you can adjust this value. So let's see if I can get to 0.45. I can't do it. So now I might toggle on this. Now you can see that I'm getting, see, so it's kind of it's a guessing game where you got to kind of toggle things on. Can't get there from here. So let's try this one. Nope, can't do that. So it really is just like, what's the best thing you can do to actually do it? So I would say whatever you can to get close to 45 milliamps at each step, that's perfectly fine. Otherwise, it's, it just becomes very difficult to go. So you can sit here all day and try to toggle things. You just can't get there because this is real world stuff. So that's why I said, just go ahead and connect this over here. And we do the two 1200s, and that's pretty good. 0.055 is about the minimum current you're going to get. So that's perfectly fine. And then all you have to do is you just have to adjust these switches in combination with this right here to get to the next value. So I would do my recording. So I would set up the table over here so I can record my voltages. So let's see, I want my E1, not the oscilloscope. I guess I have to turn that off first. Where's my oscilloscope? There it is. It doesn't seem that this is smart enough to know how to do that. So I'm going to do meter 1. I'm going to do frequency, and I'm going to do my DC current. I'm going to apply all those. So now I have the voltage, the frequency, and the current. So I could start doing some data collection. So, whoops, I got too many in here. So let's delete this one. So I've got my field current here. Now the next step that I'm going to do is I'm going to increase this to in 10 equal steps. So I'm going to go from 55 up to 90. So I'm going to toggle one of these on, and that doesn't seem to be enough. I'm going to toggle another one on. Still not enough. Let's try this. Too much. And let's see if I can actually, no, I can't get it like that. Let's see. All right, so you can see this combination here, a 300 and 1200. Let's see if I can get to 90 milliamps. So this is where you're just going to have to be doing a lot of back and forth to get to your values. And you can see here, I got 89 milliamps, which again is close enough. So I'm going to hit the record button. And then you're going to get your 10 equal steps that way. So I didn't discuss the steps of, going those values. That should go ahead and be able to get you all the way through. Oh, I forgot to mention, I should have included the speed here. So I do have the speed. So I probably should have included that. So if you want to do your data recording, you can certainly do that. Yes. Now, I said, do I want to include the speed? Well, let's check and see. Let's record that. Oh, this is power. I thought that was speed. So let me cut this one. Try that again. Oh, speed. I've looked at the wrong one. So let's record this. And now you can see 1800 RPM. Now, my question for you is there any other data on this chart that would allow me to calculate what the speed of operation is? How's this? Is it a good or a bad thing? Having both screens at the same time? Is it too hard to see or?
That's good.
Okay. So I'm going to go ahead and bring up whiteboard. And remember our equation, our speed N is going to be equal to our frequency multiplied by 120 divided by the number of poles. This is a 4-pole machine, and how we know that, because when we had 1800 RPM, we confirmed that F was equal to 60, so we'll substitute that and we divide by P. So P is equal to 4. So this is a 4-pole machine. So if we want to, we can confirm that our 60 hertz gave us 1800 RPM. So really, in a synchronous machine, once you know what the frequency is of your output voltage, you actually can very quickly determine what the speed is. So let's see with the lab. So you can do all these connections. Then you can short circuit R1 and you can set the prime mover speed to 0, turn it up. You can do all that stuff. You can get the frequency, calculate the theoretical frequency. This is that equation we just did. Now you're going to obtain a graph of synchronous generator output. What I'm looking for over here is the open circuit characteristic. And if you remember the open circuit characteristic, it's a plot of field current versus our open circuit voltage. It should be flat until it starts to get to higher current values of field current, and you can get that value there. Okay? So that should get you all up to step 18. Any questions? And I'll give you another 10 minutes or so to get through step 18. The hardest part about this step is, well, 2 hard parts. First one is just toggling the switches to get the current values you need. And then the second one is just exporting the data into Excel. If people want to see me export the data in Excel, I can certainly go ahead and do that. But I'll do that offline here. All right, so I'll check back in at 1:50. So I'll pause the recording and give you about 10 minutes to get this done. So unless there's any questions. Okay, give you 10. Okay, how you all making out? Get all your data points? Do you still need more time?
I'd like to think I have all them. Could you do just one real quick, just to make sure I have the correct kind of way to
Do
get the
one
data, excuse
what?
me. Do one data point.
Do one. Well, let me put this up real quick. I'm not quite following your question, but let's see if this meets your request. Okay, can you see the metering screen?
Yes.
So here's one data point. I have E1. I have the frequency. I have 444 milliamps, which to me is close enough to 450. And I have the speed. So I just click
Okay.
record.
Okay, perfect. I just wanted to make sure I was doing it correctly. Thank you.
Okay. All right. So then the last thing is I'm going to short everything out. So this is the wire that comes in from the DC field. So I'm going to go directly over here because all I've got to do now is go right into the meter. And I can see that the maximum amount of current that I can drive is 0.927. So I'm going to go ahead and record that data point here. And this is the table that I have. So you can see these are about 45 milliamps apart, more or less, pretty close. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, evenly spaced. Obviously, I didn't include 0 because there's nothing there. And then I stopped at the absolute maximum, which is 927. So does anybody need any help from how to plot this correctly? It's pretty simple, but does anybody need any help?
I'm all set. If
I'm good, thanks.
I might be the only.
Okay. All right. So all you have to do is export this data and you should be able to get the curve. So the next thing we're going to do, so you can go ahead and you can, when we have a moment, you can do this. So you can answer or do problems or section 17, 18. Now all we need to do is start off on 19. Does anybody need me to see how to do steps? I'll show you really quickly how to do it. So yeah, I'll just do it really quickly. It shouldn't be too bad. So all we need to do is we're going to adjust this to 300 milliamps. We can't get there from here. So I'm going to take this wire again. I'm going to run it through here. And I'm almost at 300 there. I'm not perfect. So let's see if I take off one of these and then can I tweak it to get to as close to 300 as I can. Okay, that's pretty close to 300 for me. So you may want to have exported your data, or you may want to do an additional data point to do the speed adjustments. But at this point now, you're going to use the built-in prime mover brake control, and you're going to start this out at 200. Hit enter, and you'll see the speed will drop. And you got to make sure it stables out, right? Because it is going to try to hunt a little bit. And then you can record your data. So you're going to do the 200, you'll do the 400, all the way up to 2000. And then you're going to go ahead and do the plot of synchronous generator output voltage as a function of speed. And that's it for the lab. Questions? Okay, well, I'm going to pause the recording, but if there are more questions, I'll stick around. If anybody needs, they feel like they have enough information, they're welcome to drop off the lab, but I'm going to stick around and answer any questions. Any questions at this point before I pause the recording?
I'm all good, thanks.
All right, here we go. Pause and you can collect the rest of the data.